This is B. Naresh, working as assistant professor in ECA department. And today's topic is rectifiers with capacitive filter. So in the last sessions, we observed that the rectifiers. So in that, we observed that half wave rectifier and full wave rectifier, as well as bridge rectifier. So means that we know that the rectifier means it converts the AC signal to the pulsating DC signal. So for that case, the rectifiers are designed with a PN junction diode, and based on the operation of the rectifiers, we defined as three types of the rectifier. One is half wave rectifier. The second one we defined as full wave rectifier, and the third one we defined as bridge rectifier. So in that half wave rectifier, it allows only the one of the given clock of cycle. Means when you're passing like this, based on the utilization of the diode, let us take this is your input signal. If this input signal is passing through half wave rectifier circuit, it allows either positive portion of the given input signal, or it allows the negative portion of the given input signal based on the utilization of the diode in the circuit. And based on that, we identified the ripple factor. So this is the most important. The ripple factor is calculated or determined in all the three rectifiers rectifiers here. So in this half wave rectifier, the ripple factor is represents as 1.21. In a full wave rectifier, the ripple factor is 0.47 or 48. Then in a bridge rectifier also, the ripple factor is 0. Means that this ripple factor indicates that how much ripples will be presented in a pulsating DC output. Means in a output of your rectifier circuit, it contains a DC components as well as the AC components. So how much AC components will be occurred in that rectification process, and that amount of ripples are measured in terms of ripple factor. So based on these three representations, in half wave rectifier, the amount of ripples are 1.21%. Means in a full wave rectifier, the amount of AC ripples are 0.48, and similar to the bridge rectifier. Then our aim is we need to reduce all the AC components of your rectifier output. We need to use the filter concepts. So here the filter is defined as, so means the filter is used to remove the unwanted AC components, or to remove the ripples of a rectifier output. We need to use a filter concept. So that is the reason. And based on these filter concepts, now we are going to show that the maximum AC ripples we are going to reduce from the rectifier circuit. We need to maintain a DC output voltage, but it's not exactly possible to produce exact DC level. But the aim to be, we are going to reduce a more number of AC components of the rectifier. Means we are going to minimize the ripples from the pulsating DC output. So for this case, we are going to use that a filter concept here. Based on that filter concept, we have that different types of the filters concept here. One is designed with a capacitor, hence that filter is called as a capacitor filter. And while using this process, means while to provide this processing, means to eliminate a more number of AC components from the rectifier output, then we can use either a capacitor, or we can use inductor, or by the combination of capacitor and inductor, and that is nothing but your a L section filter or a pi section filter. So that is the reason this is pi type filter. So hence, whenever the circuit uses a capacitor, means or the rectifier output is passing through a capacitor, and that type of the filter is called as a capacitor filter. And when the rectifier output is passing through inductor, then the type of the filter here it is called as a inductor filter. And by the combination of inductor and a capacitor, it is called as a L section. And again, with a combination of two capacitances and one inductor, it is also called as a CLC filter or a pi-type filter. But in this session, we are going to discuss on the only the rectifiers with the capacitive filter. Let us consider. So, if you observe the of your rectifier, and we know that this of your rectifier contains a step-down transformer, and input side we are applying the primary input voltage, that is 230 volts AC source, and the frequency is 50 Hz, and output of the secondary winding is passing through the diode. Let's take this is the D. Then here we are going to connect a load resistance RL. So across this RL we are measuring the output voltage. This output voltage here it is acts as a off-wave rectifier output, and this circuit produces, means whenever we are applying this a sinusoidal input, and let us take this is the Vi, and input signal is varies with respect to time period, and it is represented as Vm, and this is 0 to t1 and t2 duration. And we know that let even in a 0 to t1 duration, and whenever we are passing this input signal through this transformer, and during the interval of 0 to t1, the Vi is represented as Vm sine omega t, and this signal is passing through the anode of D, and this is anode, and the cathode is connected to load resistance and with respect to the ground potential. And whenever this magnitude is passing through the anode of the diode, and we know that diode becomes forward bias, hence we can say that diode is acts as a short circuit. So whenever the diode is replaced with a short circuit, the maximum amount of current is flowing through load resistance, hence the output is also, means the voltage drop across the load resistance is equal to your given input signal. That is the reason V0 is represented as Vm sine omega t during the interval of 0 to t1 time period. Similarly let the t1 to t2 interval, and let us consider the Vi is, so under this duration, and your given input signal is represented as minus Vm sine omega t. Under this condition, and means that a negative signal is passing through anode of the diode. For this case, diode is acts as a reverse bias. Under this condition, we know that when the diode is acts as a reverse bias, then it is replaced with a open circuit, hence so there is no flow of current from this node to the load resistance. Under this point, the reverse curve, means I is represented as a 0, hence the output voltage across this off-wave rectifier is also represented as a 0. Hence, if you are drawing this output voltage, the T1 to T2 duration, the output voltage is represented as 0. Based on that, it contains some magnitude. It also contains the ripples. So from that, we identify the ripple factor of this off-wave rectifier is 1.21. And here, so similarly, in the ripple factor of full-wave rectifier, means if you want to allow both the cycles, either 0 to T1 interval or a T1 to T2 interval, then we use that full-wave rectifier as well as bridge rectifier. Based on that, we also identify the ripple factor of either full-wave rectifier or a bridge rectifier is represented as 0.47. If we observe these two, the ripple factor, means this ripple factor indicates that how much AC ripples or AC components is occurred on a pulsating DC signal. To minimize this amount of ripples from the pulsating DC output, means we are going to reduce to approximately to zero, or this 0.47 is also going to be reduced to approximately equal to zero. For this case, we are going to use a filter concept. For that filter concept, I'm going to use a capacitor, and by adding this capacitor at the end of the half wave rectifier or a full wave rectifier, or you can also use as a bridge rectifier circuit. And then we will discuss how this capacitance to reduces the AC components from your full wave, either any one of the rectifier. So if you want to observe this one, so we need to first means, so if you want to observe this rectifier concept, means you can consider any rectified circuit. So here I'm going to take, this is a rectifier. Either in the place of this one, you can use either half wave rectifier, or you can use full wave rectifier, or you can use bridge rectifier. This output is passing through a capacitive element. Let's take this is the C, and now we are going to observe this output voltage, and here we need to apply a input signal, and that input signal is 230 volts and a 50 Hz AC source. It is passing through first a rectifier network, then the rectifier output. So this is the rectifier output. The rectifier output is a passing through capacitive element. Then this type of the circuit is called as a rectifier with a capacitive filter. So that is the reason. And before going to this, observe this rectifiers with a capacitive filter, and we know that the capacitor function is, it allows the AC component and it allows the DC component. And from that representation, now I'm going to consider, so that is the reason. Here I can take any rectifier output. Either you can take a half wave rectifier, or a full wave rectifier, or a bridge rectifier that is passing through capacitor along with the load resistance. Then we are going to measure the output voltage. So for this case, to see what happens, let us consider. So if you are assuming a full wave rectifier, let us take, suppose if I am going to take a full wave rectifier, the full wave rectifier uses the center type of transformer, and it is, so the load resistance is connected across, and it should be connected to ground, and it is also connected to ground. Let us take, this is the load, and this is D1 and D2, and let us consider this is the VI. So for this, so here I consider this is full wave rectifier circuit, and let us consider, and when we are passing the input signal, and this is the VI, the time interval is 0 to T1, and this is T2. So during the 0 to T1 interval, so this is whatever, this is plus, minus, and again this is plus and minus. And for this case, during the interval of 0 to T1, so what happens here, the D1 becomes, means this is positive magnitude is passing through D1 of anode, hence under this condition D1 is acts as a short circuit, means on, and here what happens, this polarity becomes negative due to this center type transformer, this polarity becomes negative, hence D2 becomes a reverse bias, or it is also represented as open circuit. And during this 0 to T1 interval, and due to the applied input voltage 0 means Vm sin omega t, D1 is acts as a forward bias and D2 is acts as a reverse bias, hence The diode D1 is replaced with short circuit, and the diode D2 is replaced with open circuit. So if the diode D2 is open circuit, hence the maximum current flowing through the D1 towards the load resistance, hence so the current flowing across the load resistance is the same direction, hence it allows the maximum current is passing through the D1 path and towards the load resistance. Similarly, if you assume the during the time interval, the T1 to T2 interval, so in a T1 to T2 interval, the input voltage is represented as minus Vm sine omega t. So whenever this minus of Vm sine omega t is passing through D1, so what happens under this condition? The at this point now diode D1 is acts as a forward reverse bias. So why? Because the magnitude is the negative magnitude is passing through anode of this D1. Hence, D1 is acts as a open circuit. Similarly, this magnitude, this node is a negative, and this negative. So this negative and the negative magnitude becomes a positive. Hence, the positive magnitude is passing through anode of the D2. Hence, at this voltage, D2 is acts as a forward bias. Hence, it is replaced with a short circuit. Hence, the maximum current now passing through the short circuit path, that is D2, towards the load resistance. Here, the positive peak cycle and the negative peak cycle, the current flowing direction across the load resistance is the same. Hence, under this T1 to T2 also, it allows the same amount of output voltage. Now, this is a full wave rectifier out. So, for this case, now we are going to pass through the capacitor. So during this interval, so what happens initially? If let us consider, initially capacitor is fully discharged. Capacitor is fully discharged. So during this at 0 to T1 interval, the input is going towards the a positive peak. Hence, so capacitor is also acts as a charging towards the maximum voltage. At this point, the capacitor is also charging towards the maximum voltage. So now I'm going to take. So at this point, now capacitor is also, now let us assume that the capacitor is also like this charging towards the maximum voltage. Now, whenever the input voltage is reached to the Vm, the capacitor is also charging towards the maximum voltage. At this point, now you can observe, now your input voltage is decaying towards the minimum voltage. At this point, now the capacitor is also discharging towards the minimum, means the capacitor is now slowly discharging towards this path. While discharging this path, now again we are applying this one. Again, your input is suddenly changes from 0 to Vm. Now what happens at this point? So now again when you are applying the amount of voltage, now the capacitor is again charging towards. So from this point, so that is the reason. From this point, now again the capacitor is charging towards the Vm. So again when Va is decreasing towards 0, capacitor is slowly dips. That is the reason. This waveform shows so that is the reason. This waveform shows from initially charging from this voltage towards the maximum voltage. Then whenever the input is suddenly falling towards the minimum, then capacitor is also slowly discharging towards the minimum. While discharging towards the minimum, again we are applying the input voltage. Hence, the capacitor is again charging from this discharging points towards the maximum voltage. So this is means this amount of, if you observe this graphical representation, whenever this rectifier output is passing through the capacitive element, this amount of AC components will be removed from that filter concept. So that is the reason. So by using this capacitive filter, we are reducing the more number of ripples from the pulsating DC output or rectifier output. Now we'll see in the mathematically how it is ripples will be how amount of ripples will be reduced. For this case, let us consider from this graphical representation or from the analysis of capacitive filter. So here I use that. So means let us assume that this is the charge is acquired toward the maximum, and again at this point the capacitor is discharging. Means this point here, this point is called as the charge has lost or a discharging path. Let us consider here we have the equal amount of the time periods, means the charging time period and the discharging time period. Hence, I am going to assume that the charging time period is equal to discharging time period. So here we know that the based on the capacitor principle, we presented as the charge is represented as Q is equal to represented as C into V. So that is the reason. Here I represented the charge. How much charge is acquired during the pulse during the when the input signal is rising from 0 to maximum voltage. The capacitor is also rising towards the maximum voltage, and that charge is represented as in terms of C into V. So here the C and the V means the V are peak to peak voltage. I consider that the ripple factor peak to peak voltage. And similarly, and here we are capacitor is discharging towards the whenever the input is discharging towards the minimum voltage or decaying toward the minimum voltage. The capacitor is also up at this point. The capacitor is fully charged. Hence, now capacitor is also discharging towards the minimum voltage. While the capacitor discharging towards the minimum voltage, it loses the amount of charge. That loss in terms of is represented as IDC into T2. Hence, we are going to assume they are the parameters. The charging time is equal to your discharging time. So hence that is the reason it is represented as VR peak to peak C is equal to IDC into T2. Now I'm going to calculate. So in this case, what happens means if the value of the capacitor means we need to maintain if at this point if you observe this graphical representation, and here the capacitor is slow means the capacitor is slowly discharging towards the minimum voltage. So means if you want to allow this type condition, we need to maintain the capacitance should be very large. That is the reason. If the value of the capacitor is very large or the value of the load resistance is very large, then we can assume that the T2 is equal to the half of the periodic time of the waveform. So hence from that I represented as the T2 is represented as half of the time period, that is T by 2. So we can also write the reciprocal of the time period is nothing but a frequency. Hence, so here this reciprocal of the frequency again is represented as your time period. Hence, we know this one. So we assume that the charging time is equal to discharging time period. So what is the charge time? The Q is attained to the maximum voltage. That is represented as C into VR peak to peak. That is equal to IDC into T2. So here I am going to substitute this. So here assume this one IDC into T2, and now we assume that the T2 is represented as 1 by 2F. So hence this is 1 by 2F. That is the reason. From this point, we can write this VR peak to peak C is equal to so IDC by 2F. So and this is 2F here. And from this, here I am going to calculate this VR peak to peak is equal to IDC by the C is getting here. So means 2F into C. So that is the reason we assume this one. The VR peak to peak voltage is equal to 1 by 2 times of IDC by FC. And from this, now we are going to calculate how much ripple will be generated during this filter operation here. So let us consider. So for this graphical representation of the capacitive filter, so it looks like the output of the capacitive filter is looks like, means this is the output of the capacitive filter, and means the charging and discharging time periods. So it looks like, in general, this waveform or this graphical representation is looks like a triangular nature. Hence, the RMS value of the triangular is represented as VR peak to peak by 2 root 3. And here we observe this VR peak to peak in a previously. So what is the VR peak to peak? We observe that is IDC by 2FC. Now I'm going to substitute this VR peak to peak value in that to observe the triple factor by using the a triangle nature. So hence here I'm going to calculate that. So this VR RMS value is equal to IDC by 2FC into 2 root 3, means it becomes IDC by 2 into 2 means 4 root 3 into FC. Then this is a VR peak to peak or RMS voltage of triangular waveform here. Then if you want to write in terms of voltage, so we know that I is nothing but V by R. Hence, now I'm going to replace this IDC value. IDC is equal to, can I write VDC by RL. So that is the reason this VR peak to that RMS voltage is represented as IDC means VDC by RL, means that is 4 root 3 F into C into RL. So hence, now by using this one, now we are going to calculate the ripple factor of capacitive filter, means, and from based on that we need to observe how this capacitive filter is reduces the ripples of a pulsating DC or rectifier output. So hence now I'm going to calculate. So we know that the ripple factor is defined as it is the ratio of AC component to the DC component. So just now we observed that AC component, the AC component is represented as, so VDC by 4 root 3 into FC into RL. So hence, so that is the reason VDC by 4 root 3 F into C into RL. Now the ripple factor is defined as is the ratio of AC component to the DC component. The DC component is VDC. Hence VDC is a get cancel. The ripple factor is represented as, so this is the ripple factor. The ripple factor is represented as, so what is the VRMS value? VDC by 4 root 3 F into C into RL by, again this is VDC. So VDC get cancelled. Then the ripple factor is 1 by 4 root 3 F into C into RL. And from this mathematical relation, and we have one relation, this ripple factor is inversely proportional to either capacitance, or this ripple factor is inversely proportional to load resistance. So we observe these two parameters. So from this mathematical representation, the ripple factor from this capacitive filter, the ripple factor of this capacitive filter is inversely proportional to either the external capacitance or a load resistance. Means that if you want to reduce the more amount of the ripples from the rectifier output, either we need to maintain the capacitance or load resistance should be very large. Means that if you are maintaining the C is a very large, ripple factor is going to be reduced. Or you can maintain the load resistance is a very large also, then it reduces the ripple factor. So that is the reason. To reduce the amount of ripples from the rectifier output, either we need to maintain the capacitance or the load resistance should be very large. So based on that, we can reduce the more AC components or pulse ripples from the rectifier output by using this capacitive filter. Now we'll see some of the problems on this capacitive filter rectifiers with a capacitive filter. First, we'll discuss the calculate the value of capacitance to use in a capacitor filter connected to a full wave rectifier operating at a standard aircraft power frequency of 400 Hz, and if the ripple factor is 10% for a load of 500 ohms. So for this case, we need to calculate how much capacitance is required to produce this ripple factor is 10% along with a given load resistance is 500 ohms. Hence, from this case, the given data is they given the frequency. The frequency is 400 Hz, and the ripple factor, that is ripple factor that is equal to 10%. So 10% means 0.01. For a given load resistance, that it means RL is equal to 500 ohms. Now we need to calculate how much capacitance is required to absorb this capacitance, and we have this. Just now we observe the relation between capacitive and the load resistance with respect to the ripple factor. What is the formula? The ripple factor is equal to 1 by 4 root 3 into FC into RE. Now by using this one, so here the known parameter is frequency is a known parameter and RL is also known parameter, and the ripple factor they given that 10% means. So from this all these parameters we need to calculate this C. So hence now I'm going to use. So how to calculate this one means, what are the given specifications? The ripple factor is 10% means that is 0.01, that is equal to 1 by 4 root 3 into frequency is, the given frequency is 400 Hz. Hence this is 400, and we need to calculate the capacitance, and the load resistance is, the given load resistance is 500 ohms. So hence this RL value is 500. So from this we need to calculate the C. So means how to calculate the C? C is equal to 1 by 4 root 3 into 400 into 500 into 10 per, that is ripple factor I'm taking outside, that is 0.01. Then to solve this ratio, after the solving the ratio, then it gives that the capacitance is 72.2 microfarads, that is the capacitance value. And with respect to this given load resistance and the capacitance, the full wave rectifier produces the ripple factor is only 10%, means that is equal to 0.01. Now we'll see another problem. Design a capacitor filter that meets the following specifications, that is VDC is 20 volts, IDC is 100 milliamperes, ripple factor is 0.01. Use full wave rectifier operating at the supply frequency of 60 Hz. So for this case, we need to design a capacitor filter for the given specifications. So what are the given specifications? VDC they given the 20 volts, but IDC value is 100 milliamperes. Then the ripple factor. So what is the ripple factor? The ripple factor is represented as 0.01. Now, so first we need to calculate what is our ripple factor. This ripple factor is represented as 1 by 4 root 3 into F into C into RL. Now we know that one relation. So IDC value is represented as, means IDC is equal to VDC by RL. So in that given case, they given that IDC value as well as the VDC value. Now first we need to calculate RL. So means RL is equal to this VDC by IDC. So hence the VDC is 20 volts divided by this is 100 into 10 power minus 3 means this is 2 1 and this is 1 by 5. So this is 1 by 5 into 10 to the power of minus 3 means RL is equal to 0.2 kilo ohms. RL value is 0.2 kilo ohms here. So based on the given specifications, we observed that the RL value is 0.2 kilo ohms. Now we need to calculate the capacitance. So what is the formula? Capacitance is, the ripple factor is 1 by 4 root 3 F into C into RL. So here the ripple factor value is 0.01. 1 by 4 into root 3 into F is 60H. Then we need to calculate the C, and just now we observe this RL value. So RL value is 0.2 kilo ohms. Now from this we need to calculate C is equal to, what is the C value? 1 by 4 root 3 into 60 into 0.2 into 10 power 3 into 0.01. Now to solve this one, then it gives a capacitance value. So after that, you should draw the circuit. So means we take this full wave rectifier circuit. Then here we need to place capacitor and the load resistance. Now we need to write the load resistance value and the capacitance value. So up to this point, today we observed that rectifiers with a capacitive filter. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.